Label the most acidic hydrogen in each molecule and justify your choice by using appropriate pKa values. Now, here are 4 different compounds, and we need to find out which one of the hydrogens in these compounds is going to be acidic. Okay, now let's first consider the different factors that's going to affect the pKa value of the compound. The pKa value of the compound is going to be affected by electronegativity, and then it's also affected by size, and then hybridization of the atom where the hydrogen is connected to, and resonance of the conjugate ion, and inductive electron withdrawal. So these are the different factors that's going to affect the pKa value of the compound. Okay, let's also write down what is the relationship between pKa of the compound and its acidity. Stronger the acid, lower will be the pKa. And then if the acid is strong, then the conjugate base should be a weaker base. These are the 2 important relationships that we have. Now let's take a look into the first compound. The first compound has got 2 functional groups. We have a carboxylic acid group and we have a thiol. Now the carboxylic acid group has a pKa value of about 4.5 and the thiol has a pKa value of 7. Now this is a very straightforward answer. We already know that lower the pKa, stronger would be the acid. So obviously, if the hydrogen need to come off from this molecule, it would be this hydrogen first, right? So this is the hydrogen that's going to be more acidic. Now, what is the reason behind it for it to have a lower pKa value? Now, when I pull this hydrogen from this molecule, it's going to form the conjugate base. The conjugate base is going to have this structure, right? Where the negative charge is actually going to be distributed between the 2 oxygens because of resonance. So basically, the conjugate base is resonance stabilized, and we already know that if we have a weaker conjugate base, then the acid that it started from should be a stronger acid. Okay, and that is the reason why carboxylic acid is strongly acidic here, or the hydrogen, or this is the hydrogen that is most acidic here. Okay, now let's take a look into the next compound. Okay, the next compound has a protonated amine and a carboxylic acid. Okay, the pKa value for protonated amine is roughly about 10. For the carboxylic acid, it's about 4.5. Again, we already know that the carboxylic acid is the one that's going to lose the proton. Okay, here again, resonance plays an important role. So in both of these compounds, resonance is the reason for it to have a lower pKa value. Let's take a look into the third compound. The third compound also has got 2 important functional groups. We have an alcohol and we have a carboxylic acid. Between these 2, we definitely know that this is the hydrogen that's going to come off because this has a pKa value of about 4.5 and this one has a pKa value of 15. And again, it's exactly for the same reason that a carboxylate ion can be formed, which is resonance stabilized, right? So here, although we have the hydrogen that's connected to the same atom oxygen, the electrons in here are delocalized because of resonance, whereas in here, it's just going to stay on that oxygen. It has no way that it can have resonance contribution. Okay, now let's go on to the next one. This molecule has an alcohol group and also an alkyne or a triple bond, and a hydrogen that is attached to an sp carbon. So between these 2, let's find the pKa values. So this has a pKa value of approximately 25 and this has the pK value of 15, and obviously this is the one that's going to be more acidic. Okay, here the electronegativity plays a role. So remember, if the hydrogen atom is connected to an atom that's more electronegative, then that hydrogen is going to be more acidic. So here oxygen is more electronegative than carbon, and therefore the hydrogen that is attached to oxygen is going to be more acidic.